When multiple threads are sharing the same resource, your application is prone to data race and race condition bugs. Data race bugs, as we saw in the last lesson, can be solved by increasing the visibility of a resource. That's why almost all data race bugs can be solved using the volatile keyword. However, race conditions stem from multiple threads interfering with each other when operating on a shared resource. You can start by downloading the course materials from the GitHub link that I'm going to leave you inside of the video description. Once you download it as a zip, make sure that you load the final starter project for this course, race condition. And let's begin. All right, let's go ahead and open up the starter code. So here I've got two threads, thread 1 and thread 2. Both threads are operating on a shared variable called count, and they're incrementing the variable by 1,000 times. So we can expect the count variable to equal 2,000 once both threads are done with it. Is that what's going to happen? Probably not. So here you'll notice a comment where I'm saying count is non-atomic. When I say non-atomic, that means incrementing a count is not done in a single step. So let's assume that at one point the count equaled 250, okay? So count what it's going to do in 3 steps is read the value 250, okay? Then it's going to determine the incremented value 251. Then it's going to set the variable, in this case count, equal to the incremented value 251. So the count is 250, right? And this variable that is currently equal to 250, it is being operated on by thread 1 and thread 2. Okay? Now, there might be an instance where thread 1 and thread 2, they both read the count variable at the exact same time to be 250. If both of them read the same value 250, then both of them are going to determine that the incremented value is 251, which means they're both going to set the variable equal to 251, which means we lose an increment because one of them was supposed to set it to 251 and the other was supposed to set it to 252, but because they both read this value at the exact same time, we end up with an incorrect result. That is a race condition, and it happens when many threads are performing multi-step operations on a single resource. And if a shared resource is prone to a race condition, one solution is to use an atomic data type. So here, instead of using a plain old int, we're going to say atomic integer count is equal to a new atomic integer that starts with a value of 0. And inside of increment, we can't say count anymore. What we're going to do is say count.increment and get. This is an atomic increment. Unlike count++, which was a multi-step increment. And here we can return count.get. So first of all, atomic integer ensures visibility, meaning that when one thread modifies the count, the new value is immediately visible to other threads. But data racing isn't the issue here. The problem is that threads can interfere with each other when they perform non-atomic operations on a shared variable. But because count was declared as an atomic integer, in this solution, increment and get is going to be an atomic operation, meaning it's indivisible and executed as a single step. So I'm going to say executed as a single step. So if one thread is currently incrementing the atomic count, it's going to prevent other threads from intervening between the read, increment, and write steps because they've been atomized into a single step. And it's worth noting that race conditions aren't limited to just integers. Java provides a whole package of classes that provide a way to perform atomic operations on different variable types. So you've got atomic types like atomic boolean, atomic long, so on and so forth. All right, now this was pretty cool, but we can also solve race conditions using locks. So I'm going to go on the Learn the Part article, whose link I will leave you inside the video description, and simply copy the starter code. Instead of just pressing Ctrl Z. And now let's check to make sure that we still have a race condition. We indeed do. What I can do is go back up here and define a lock. So I'm just going to copy this and then here declare an object lock that equals a new object. Okay? And what I want to do is when a thread is currently performing this non-atomic operation, I want to lock this critical section in my code because I don't want other threads to be performing it as well. So I'm going to say synchronized lock and encapsulate this countless plus inside of our lock. So with this approach, when a thread enters the synchronized block, it acquires a lock on the lock object. No other thread can enter any synchronized block on the same lock until the lock itself gets released, so until the operation is finished. This ensures that only one thread can execute the increment operation at a time, again preventing race conditions. If I press run, we have fixed it and we can remove the might be incorrect string. I just want to mention that when possible, you should favor atomizing operations as opposed to locking them. Atomic operations are much faster than acquiring and releasing locks and having one thread waiting for another thread to perform its task. Atomicity is implemented at a low level, making them highly efficient. However, there are scenarios where multi-step operations on a shared resource are just too complex for atomization. In such cases, you would be forced to use a lock. It would be your only viable alternative. So to recap, when multiple threads are sharing the same resource, your application is prone to data race and race condition bugs. Data race bugs, as we saw in the last video, can be solved by increasing the visibility of a resource, which can be done using the volatile keyword. Race conditions stem from multiple threads interfering with each other when operating on a shared resource. One solution is to atomize the multi-step operation, or simply lock the multi-step operation such that only one thread can execute it at a time.